Welcome to this explainer. Today, we're going to be playing the role of scientific detectives. We're tracing the absolutely mind-bending history of the atom. It's a journey to unlock the universe's absolute smallest secrets, uncovering the clues that totally shifted our understanding of reality. Let's get right into it. All right, let's look at this staggering number. That is 7 billion billion billion, or, 7 octillion if you want to be fancy. That is the exact, unbelievable number of atoms currently making up your body. And what's really wild, about 98% of those atoms are replaced every single year, and you don't even realize it's happening. This brilliantly illustrates the sheer microscopic scale we're actually talking about here. Our universe is built on components so incredibly tiny that they just completely defy human intuition. I mean, think about it. Just one tiny drop of water has over 5 sextillion atoms. That is a 5 with 21 zeros after it. To make sense of something so vast, yet so physically microscopic, we really need to look back at how scientists figured this all out in the first place. So, to wrap our heads around these tiny building blocks, we're going to follow a timeline of breakthroughs. Because, our understanding didn't just happen overnight. Science is a messy process. Each scientist discovered a new clue that basically broke the previous model, which forced the whole world to reimagine the fundamental structure of matter. But hey, before we get to the modern era, let's establish our baseline definition. The concept actually goes way back to ancient Greek philosophy. They viewed matter as finite. They believed that if you took something and kept cutting it in half over and over again, eventually you'd hit a piece that was ultimately uncuttable. They called this atomos, which literally translates to indivisible. Part 1, the indivisible sphere. Our first major era takes us back to 1803. This is where that ancient Greek concept was actually put to the scientific test by a brilliant guy named John Dalton. He brought the idea of the atom into the lab. He basically pictured them as solid, indivisible billiard balls. He concluded that all atoms of a single element are completely identical in mass, and that different elements just have different types of these solid spheres. Now, an absolutely crucial piece of this puzzle is Dalton's law of multiple proportions. Before Dalton, people kind of thought elements could just mix together in any random ratio. But Dalton proved that atoms actually combine in very rigid whole number ratios to form compounds. Take water, for instance, H2O, or hydrogen peroxide, H2O2. You literally cannot have 1.2 atoms of hydrogen. No partial atoms allowed. They have to be whole, intact units. Moving on to part 2, finding the electron. So, for nearly a century, Dalton's solid billiard ball model absolutely ruled science. But almost 100 years later, that indivisible sphere was cracked wide open by an English physicist named J.J. Thomson. In 1897, Thomson was messing around with a sealed glass cathode ray tube, basically a tube with almost all the air sucked out. By hitting the gas inside with high voltage, he actually managed to pull these mysterious glowing cathode rays right out of the metal plates. And when he brought magnets near the tube, he noticed this glowing beam bent away from the negative plate and went right toward the positive magnetic plate. Okay, so why does this matter? Well, because we all know opposites attract, Thomson realized these particles had to carry a negative charge. On top of that, based on how easily that beam bent, he was able to calculate their mass. And guess what? He discovered these particles were thousands of times lighter than even a single hydrogen atom. Boom, Thomson had just discovered the very first subatomic particle, the negatively charged electron. The atom, as it turned out, was definitely not indivisible anymore. Now, because atoms as a whole are naturally neutral, Thomson knew there had to be some sort of positive charge in there balancing out his newly discovered negative electrons. That led him to propose the plum pudding model in 1904. He pictured the atom as this spherical cloud of positive charge, with negative electrons just stuck inside it, kind of like raisins baked into a cake. Or, if you've ever bitten into what you thought was a chocolate chip cookie only to realize it's an oatmeal raisin cookie, you can perfectly picture this model. And frankly, you can probably picture the scientific community's eventual disappointment with it too. Which brings us to part 3, discovering the nucleus. Yeah, as it turns out, that raisin cookie model was dead wrong. The plot really thickens in 1911 when one of Thomson's own students, the super extroverted scientist named Ernest Rutherford, decided to actually put this delicious-sounding theory to the test. Rutherford designed an absolutely ingenious test called the gold foil experiment. He fired heavy, positively charged alpha particles, think of them like tiny atomic bullets, at a sheet of gold foil that was just 1,000 atoms thick. Now, because Thomson's model said the atom's positive charge was just softly smeared out, Rutherford totally expected his heavy alpha bullets to just blast right through that soft positive cloud with basically no resistance. And sure enough, about 98% of those particles did pass straight through. But, incredibly, a tiny fraction, we're talking about 1 in 20,000, bounced straight back. This absolutely shocked the scientific world. It actually prompted this legendary quote from Rutherford, where he said it was as incredible as firing a massive 15-inch artillery shell at a piece of tissue paper and having it bounce back and hit you. Rutherford's conclusion from this was revolutionary, and it changed everything. To get that kind of bounce back, the mass of the gold couldn't possibly be evenly smeared out. The atom, it turns out, is over 99.9% completely empty space. Almost all of its mass and positive charge is crammed into this impossibly tiny, incredibly dense center that we now call the nucleus. To put that into perspective, if you magnified an atom to the size of a massive football stadium, the nucleus would be the size of a single tiny pea sitting right on the 50-yard line. Up next, part 4, completing the puzzle. So, Rutherford had found the nucleus, and he later identified the positively charged particles inside it, naming them protons. But our detective work wasn't quite over yet. See, the math just didn't add up. The nucleus was way too heavy to be made of just protons. Let's fast forward to 1932 to see how this builds. A scientist named James Chadwick was shooting alpha particles into beryllium atoms, and he managed to knock a completely mysterious new beam out of the beryllium nuclei. Unlike those electrons from earlier, this beam didn't bend in a magnetic field at all. That meant Chadwick had just discovered a heavy particle with absolutely zero electrical charge. Chadwick had found the neutron, and by adding the neutron to the mix, we finally had the complete roster of subatomic particles that make up all the matter in our universe. As you can see, the protons and neutrons pack tightly into that tiny, dense nucleus, making up the mass, while the practically weightless electrons handle the negative charge out in all that empty space on the outside. Finally, part 5, the quantum atom. All right, so we have the parts. But our detective story has one final major twist, and it's all about how those tiny, weightless electrons actually behave out in all that empty space around the heavy nucleus. Initially, Niels Bohr suggested this really iconic planetary model. He proposed that electrons perfectly orbit the nucleus in fixed circular paths, kind of like planets orbiting the sun, and they're bound together by really strong electrical attractive forces. However, the Bohr model was just a bit too simple. It completely failed to explain how more complex, multi-electron atoms behaved. It took Erwin Schrödinger and the quantum physicists to realize that electrons actually don't act like standard solid objects at all. They actually move in waves. What that means is we literally cannot ever know their exact path. Instead, as the currently accepted quantum mechanical model shows us, electrons exist in these fuzzy clouds of probability called orbitals. We really only know where they are likely to be found. So, what's the big takeaway from this explainer? It's that our physical reality is deeply, deeply strange. I mean, despite being made of 99.999% empty space and fuzzy probability clouds, atoms somehow form the solid matter that we interact with every single day. And why is that? It's because the electrical forces gluing those negative electrons to the positive nuclei are impossibly strong. We're talking 10 to the 33rd power times stronger than gravity. That is a 1 with 33 zeros. Those extreme forces are the ultimate atomic glue holding everything together. Which brings us right back full circle. I'm going to leave you with this final, truly mind-bending thought to ponder today. If the 7 octillion atoms making up your body and the screen you are watching this on are essentially 99.999% nothing but empty space held together by invisible forces, what does solid even mean anymore? Thank you for exploring this incredible atomic detective story with me. Keep questioning the universe around you.